which implies that in order to reach the same error, you need only half the window. So, and this is because we did an assumption that we have knowledge of lambda f or lambda n. As you know that u is a function of lambda f and lambda n. So basically assuming that you know one of them is like assuming have the information. We drop this assumption later and I'll show the results for that later. All this time I've been talking about the estimation of the duty cycle, and also you want to look at the estimation of the other traffic parameters, the average on time, the average on time. So for the estimation of lambda f and lambda n in literature, Kanchin, they already had derived the maximum likelihood estimators for lambda f and lambda n. Lambda n is the average, lambda f is the reciprocal of the average off time, and because the samples you take are in discrete time, so it's not as simple as estimating u. That's why they had to use maximum likelihood estimation. So we went further and calculated the Kramer-Rao bound on their estimator. And again, it's given by the inverse of the future information, and it's this expression here. Again, if you take the limits as n goes to infinity, you get this expression, which basically says that, again, for a fixed window, you have a lower bound because of sample correlation. And so this is the Kramer-Rao bound for estimating lambda f and estimating lambda n. And the next and final step would be the joint estimation of all traffic parameters. So for that, we derived the Kramer-Rao bound for the joint estimation of lambda f and u. Note that lambda f, u, and lambda n are dependent, so estimating any two would enable you to estimate the third parameter. We derived the same expressions for lambda f, lambda n, and u and lambda n, but they are in the appendix/publication. So the problem here is you want to calculate the Kramer-Rao bound, but now it's for two parameters at the same time. So the Fisher information is 2x2 matrix, and you have double derivatives and so on. So this part is we derive the error in estimating u by this expression here, and this is the error as n goes to infinity. And the good news is these expressions are the same as the weighted sampling case that Chunhao derived. And so basically this is the Kramer-Rao bound when you don't have knowledge of lambda f or lambda n. And if you compare it with the expression where you know lambda f or lambda n, same error in half the observation window.
I have a question. In practice, do you know on that? Or
maybe in some, okay, so in literature regarding this work, people usually assume that you know one of the three parameters. In a practical situation, maybe you are in a situation where you know the average, for example, the average length of a packet that you transmit. For example, if text messaging or one of these systems where you have a packetized system, you know the statistics for that. Maybe you would know lambda n by then. And this is the expression for the error in u, and this is for the error in lambda. And as you take the limit as n goes to infinity, again, you have a lower bound. Now I'll show some numerical results. Here, this is for the estimation of u. This is total number of samples. These three lines are basically uniform stream, non-uniform stream, averaging, and the Kramer-Rao bound. So as you can see, even if in math they don't really quite match, but in reality the gap is very small, you cannot see the difference. This here is the analytical results on when you have spectrum sensing errors, and this here is the Kramer-Rao bound, assuming knowledge of lambda f. In this scenario, we assume that the observation window is long. By long, I mean long relative to the average off and on time. So the product of T lambda f is 25 in this case. This slide, in this case, I assume that the observation window is shorter. So you have higher correlation between your samples. And the results are quite interesting. If you look at the blue lines here are averaging of uniformly sampled stream. And the result is counterintuitive because increasing the number of samples increases your estimation error. This is because you have a fixed window. What you do is when you increase the number of samples, you make the samples more correlated. So you end up with actually worse. So basically the idea is, well, if you have a very short observation window compared to your average off and on time, you better end up with lower number of samples. Higher number of samples wouldn't do you any good. This is not the case for non-uniform sampling though. As you can see, it's the red line and it almost coincides with the Kramer-Rao bound. But here I'm assuming that I'm using the optimal the optimal sampling sequence. And this is because for what would happen in this case is the optimal sample sequence will basically get rid of the samples on the edges and weight them. So you end up with a solution for the correlation problem. And this is the Kramer-Rao bound, assuming no lambda f. This result shows the error in estimating lambda f. These are the Kramer-Rao bounds with knowledge of u, which is typical in literature. People did that, they assume knowledge of u, and without knowledge of u. Sorry, with knowledge of u, without knowledge of u. And these are these inverted triangles. These are the maximum likelihood estimation, and the other simulation results are when you introduce spectrum sensing errors. The last figure, this is basically the error in estimating u as a function of the actual value of u. And this figure is important in algorithm design. If you want to design an algorithm that would estimate u, the duty cycle that is, you better know how the error looks like as a function of u. Here, this is Kramer-Rao bound assuming knowledge of lambda f, no knowledge of lambda f, and spectrums with spectrum sensing errors. Not the Kramer-Rao bound, but the expression for the error for averaging. As you can see, the figure is not symmetric, it's a little bit skewed to the right, and that's because here you're increasing u, but we're assuming that lambda f is constant. So what happens is, as you increase your u, lambda n decreases, you end up with more correlation, so the error increases. Using this result, we designed an algorithm for the estimation of the duty cycle, and basically this is how it works. The target is you want to estimate u with a certain target root mean squared error in the estimate. So what you do here is you take n samples, an initial number of samples with initial arbitrary sensing periods. You calculate the duty cycle. You calculate the mean squared error using the expression that we derived earlier. And you look at the worst case scenario, the worst case error. If it's below the threshold, you stop. Otherwise, you take a new sample. And when you take this new sample, you have to put sample correlation into consideration. So what we do is this new sample is taken after a period of time given by the estimated u divided by lambda. Well, in this algorithm, we assume that lambda is known, but in the publication we show other algorithms where we have blind joint estimation. So you take this sample after u estimate over lambda multiplied by alpha, and the reason why it looks like this, we use the expressions that we have to calculate the decrease in the mean squared estimation error when you add an extra sample, and this is how the expression looks like. Some constant minus some constant multiplied by e to the negative alpha. So basically this alpha is a tweaking parameter. If alpha is high, the estimation error decreases more when you add an extra sample, but on the other hand you spend more time sensing, more time trying to estimate the traffic. And these are the results that we got. Here the target RMS root mean squared error is 0.1, and this is the variation of the duty cycle. Because you are targeting the worst case error in this case, that's why the resulting error looks pretty much like the function between the estimation error and u. And as you can see here, the algorithm gets an estimate for u, and it always satisfies the constraint that you want to estimate u so that the resulting error is less than 0.1. And these are the results for different values of alpha. This here shows you the total observation window length. As you can see, as alpha increases, obviously your total observation window length increases. This concludes the last part of this talk. So the findings we have regarding traffic estimation of primary users. In this case, again, I would stress, we are talking about stationary traffic of one primary user on a channel. If you want to estimate the Curie cycle or the mean off and on times, there is an impact of the sample correlation, and which causes there to always be a lower bound on your error. And if you have spectrum sensing errors as well, they will cause, they obviously increase your estimation error, but the impact of them can be decreased by increasing the number of samples, unlike the part due to correlation. The only way to solve the correlation problem is by increasing your window length, not the number of samples. Also, we showed that having a priori knowledge of lambda f or lambda n provides much more information if you're trying to estimate u, and decreases the required window by half to reach the same error. And finally, weighted averaging, thanks to Chunhao, it achieves the bound, the Kramer-Rao bound. So the summary of contributions of this talk, we first presented mathematical framework for multi-stage sensing algorithms. We then showed how the performance, that is throughput and collisions, can be improved if you put into consideration the traffic of the primary users. And then the last part, we showed the accuracy bounds on estimating the primary user traffic. And for the acknowledgement, I'd like to thank Caltrans, Broadcom, and UCD Grad Division for funding. And Przemysław Pawłowczak is now back in, he's in Berlin, from Fraunhofer, postdoc. He was a postdoc here, worked a lot together, and Chunhao, of course. And shout out to Course Lab. Yep, so questions?
Okay, thank you.
Oh, no questions?
Let me ask the audience to step up.
Everyone.